Hi class, welcome back to Electromagnetics. We're going to start part 6 with this lecture. So we've pretty much given a pretty thorough examination of Maxwell's equations, both in free space and then in various mediums. So now we want to kind of expand from there and start to look at some more different situations. Thought for today comes from Isaiah 30:21. It says, "Whether you turn to the right or to the left, your ears will hear a voice behind you saying, 'This is the way, walk in it.'" And of course, to the Christian, when we see this, we think of the Holy Spirit, that this is the guidance of the Holy Spirit, or our conscience, or whatever you might call it, that this is the prompting of the Spirit guiding us. And even though we try to get off the path, it'll always try to direct us back to the path. Which to me, this is pretty applicable to what we're looking at today, gradients. So gradients is a methodology or a tool, mathematical tool that we use in electromagnetics to find the path of least resistance, you might say. So pretty applicable to that, and interesting thought for the day. So again, part 6, we're going to start to venture off the path a little bit away from Maxwell's equations and look at some different scenarios. So today we want to talk about gradient and electrical or electric potential. So up to this point in the course, we've pretty much been working with time varying fields. That is, our fields vary with time and position. But we now want to change gears just a little bit and take a step back and look at, now that we have Maxwell's equations, apply this back to static fields. That is, fields that don't vary at all with time. And we want to see how this relates to traditional circuit analysis. So we're going to trying to work our way back to some of the more mainstream things that we've already been exposed to in physics and circuits class. After this, we'll take a look at special class of fields that, though they are varying, the frequency is still low enough that we can still treat the fields, at least to some degree, and their effects as if they were static. And then finally, we'll introduce the approach on how to deal with higher frequency fields and traditional circuit analysis utilizing the concept of transmission lines, which is a very broad topic that doesn't really matter what branch of electrical engineering you go into, whether it's digital electronics, power, communication theory. You're always going to have these issues and take into account effects of transmission lines. So since static fields do not vary with time or anything else for that matter, except maybe location, this means that the derivative or the time derivative of anything in these equations has got to be equal to 0. So if we take that into account, we have Ampere's law and Faraday's law. Well, with Faraday's law, we'll see that the curl of the electric field must be equal to 0. And then with Ampere's law, the curl of the magnetic field is just going to be equal to the current density. So this indicates then that the curl of a static field must be 0. If the curl of a vector is 0, then that vector can be expressed then as the gradient of a scalar. And so since the curl of the gradient of a scalar is identically equal to 0, that's the reason why we say this. So to show this, we want to consider a scalar. We'll just call it arbitrarily phi, where the gradient of this vector then is defined as del phi. And so what this looks like then, del phi, is we take our del operator, which is just the partial with respect to a variable in the unit direction of that variable. We've looked at that several times before, and that's multiplied times the scalar function. So the scalar function can still have variables in it, but it just doesn't have any direction associated with it. So when we do that, what we're actually saying is we're taking the partial of phi with respect to x and putting that in the x direction, the partial with respect to y, and putting that in the y direction, and the partial with respect to z, and putting that in the z direction. So from this, the result is a vector. We can now take the curl of the gradient of phi as follows. We can go back to our operator. So if we're going to take the curl, that's del crossed with our new vector, which is just the gradient of phi. So remember, we've done this before. So the top row, we just put the unit vectors. The second row, we put the derivative operators in each of the directions. And then in the bottom row, we put the x, y, and z components of our vector, which is just the derivatives in those respective fields. So by definition, we're saying that this must be equal to 0. Therefore, this could satisfy the condition to be a solution for Maxwell's equations for our static field, because that's what we said is the curl of the vector must equal to 0. So by definition, this should satisfy that condition. So now we want to discuss the interpretation of the gradient. So to do this, we're going to take a look at the gradient of phi dotted with differential length dl. So when we do that, get my pointer here, we have our differential operator, our gradient here, and then this will be dotted with the differential x in the x direction, differential y in the y, and differential z in the z. So when we multiply this out, then we just get the derivative with respect to x, dx, derivative with respect to y, partial with dy, and so on with dz. And so we can just rewrite this then as just the derivative of phi, d phi. So to better understand physically what this means, we want to look at an illustration now. So we're going to consider some surfaces. So this first surface is an equipotential surface. So that means that the potential everywhere on this sheet is the same. It's a constant. And then we're going to have to add a second one that is going to differ by some d phi, some different amount. So it's this one's phi sub 0, this is phi sub 0, plus this differential amount as shown. So we'll now define this point P on the first surface. So examining the relationship to the other points Q1, Q2, etc., we see then that this gradient at the point is just equal to the magnitude of that value, that vector value at the point, and then just in the with the direction AN, so this unit vector. If we now consider another point Q located on the second plane as shown here, we can now express d phi as the following. And I'm take into account that we have this dl and this alpha, which is the angle between the normal to the plane and the angle that this vector will make going from P to Q. So when we look at our derivative of phi, defined as this the gradient evaluated at a point dotted with this dl value, we just demonstrated on the previous page that that's the same thing as the magnitude of the vector times the vector, the unit vector normal to the plane dotted with that differential length. And so to take this dot product, we can just take the scalar value of dl, that is the length of that vector, times the cosine of that angle between it that we looked at. So where dl cosine alpha is the shortest distance between the two surfaces along AN, hence the shortest distance between them. This means the gradient then identifies the direction with the maximum rate of increase. So this is important. This also means that the gradient can be used to find the unit vector normal to a plane at a point. So that's incredibly useful. So the first couple of lectures when we were doing vector operators and reviewing vectors, we found a way to do that. But now if we use a gradient, this is a much easier way to find that unit vector. So what does this mean to us in terms of electromagnetic fields and Maxwell's equations? Well, since E dot dl the electric field dotted with some differential length, must equal to 0 over these entire surfaces. No work would then be involved to move a test charge from one point to another on the same surface. This also means that the potential, or in this case we can start thinking of voltage, that means is equal across these surfaces. Hence we call these equipotential surfaces or equipotential planes. If we move a test charge from one plane to another, though, but being that those potentials are different, then we'll experience a change in potential or an electric potential difference. So we can note this change in potential or potential differences as the following. So at a point we have, compared to some reference O, this voltage at A would be equal to the line integral from A to our reference point 0. So this is the voltage in relation to 0. So it's E dot dl. Or if we flip the limits of integration, it'd be we flip the sign of the integral. So if we have 2 points, arbitrary points, and we still have our reference point 0, then we could find out what the potential difference is between A and B. Of course, we could take the line integral between them, but if we don't have enough information to do that, we could still use our reference point. So we could say that the integral then from A to 0 minus the integral from B to 0. So we have the potential difference going from A to 0 and then from 0 to B. That would still give us the total difference between the 2 points. And so we could rewrite that then as in just the voltage at A minus the voltage at B. So hopefully this is starting to look a little more familiar from what we've looked at in circuit analysis. And so just to get a graphical representation of that, here's our equipotential plane with VA, our equipotential plane with VB. And so if we move from one plane to the other, it's going to take some work, which will be able to work back to the potential differences or the differences in voltages at those 2 planes. So we can now extend this idea to consider 2 points A and B, which are separated by an infinitesimal length dl. We can express this incremental potential drop from A to B then as this incremental dV is then equal to the negative electric field at A dotted with that differential length that we have to travel between the surfaces. Well, we know from previous slides that this is also equal to our gradient of the voltage at that potential at that point A, which now allows us to rewrite this then as we can take both of these, since they're both equal to dV, we can set these two equal to each other. And so now we're coming to a very important relationship here, and that is this, that the electric field intensity vector is just equal to the negative gradient of the voltage. So that means the static electric field, I should say, is the negative gradient of the electric potential. So this is an equation now that gives us a relationship between electric field intensity and voltage. And so this is, like I said, we're starting to work our way back into the circuit analysis lingo that we're hopefully familiar with. But I'm kind of hoping that you'll see now that we've started from the ground up and worked back to that point. So now you see we've kind of lifted the hood and you see what's really happening under the hood of what's going to get us back to voltage, the definition of voltage and potential difference. So let's look at a quick example of how we use the gradient to find that normal vector that we talked about. So we want to find a unit vector that's normal to the surface y equals x squared at this point 2, 4, 1. X equal to y equal 4 is equal 1. Again, by using this concept of gradient of a scalar. So first we want to rewrite the equation. We subtract y from both sides, and that gives us x squared minus y equals 0. So when we do this, this now allows us to define our phi of x, y, and z is just equal to x squared minus y. So the gradient then of the constant scalar function is now given by this equation, which just means we're taking the gradient of this function we derived up here. So when we do that, we have to take the partial with respect to x and put it in the x direction, the partial with respect to y, put that in the y direction, and partial with z in the z direction. Well, since there's no dependence here on z, this term goes to 0. If you take the partial with respect to y of this, it's just -1, so that's where we get this negative ay. And the partial with respect to x here is just 2x. So we get the 2x ax minus ay. So now they want us to evaluate this at the point 2, 4, 1. So when we plug in 2 here, that gives us 4ax. And 4 doesn't matter because there's no y dependence here, so it's just minus ay. And so that gives us the vector in the direction normal to the plane, but to get the unit vector, we have to take the magnitude of this and divide by it to get us to get the vector magnitude equal to 1. So to get that, we take the sum of the squares and take the square root. So 4 squared is 16, -1 squared is 1. That gives us, add those together, gives us 17. Take the square root, so we divide everything by square root of 17. And so this gives us the unit vector now in the direction normal to this plane.